Welcome, students, to our first adventure recording some video. Today's lesson involves thermodynamic concerns for equilibrium. And remember, in thermodynamics, we're looking at the flow of heat and energy as a chemical reaction proceeds, and we're always looking at a spontaneous flow from reactants to products. And if it's carried out at a constant temperature and pressure, it is easy to quantify. Now, remember from the past that delta G is Gibbs energy. When delta G is less than 0, that particular reaction will be spontaneous, which means it will flow from beginning to end without any additional input of energy. So if delta G is less than 0, then delta G will be negative. Now, at equilibrium, when no energy is flowing in or out, the system is in balance, delta G is equal to 0. So think of Gibbs energy as energy that's available in a chemical process to actually do work. And think of the temperature multiplied by the change in entropy. Entropy, again, is the randomness of a system. When we multiply the temperature by the change in entropy, you will end up with a value of energy that is discarded in the form of heat. It is not available to do work. Only delta G in a chemical process is available to do useful work. Now, this also is available in a physical process as well. So we are going to look at an equilibrium expression for reactions in the gas phase, and we're going to consider a system where it's isothermal, meaning that the temperature is not going to change. So if we look at an ideal gas and we're changing it from pressure 1 to pressure 2 at a constant temperature, we know a mathematical relationship exists where the delta G, Gibbs energy, is equal to the change in H minus Ts, H being enthalpy, S being entropy. And the equation we've come familiar with is delta G is equal to delta H minus T delta S. Now at a constant temperature, when we calculate delta H, we know if temperature is not changing, then we know this will be 0. That means delta H will be 0. So in this equation number 1, at a constant temperature, delta H is indeed 0. And if delta H is indeed 0, now we can eliminate that term and end up with the equation delta G, the change in free energy, or Gibbs energy, is equal to minus T, the temperature, times delta S. And the temperature is expressed in Kelvin. So for an isothermal process, again, involving a single gas undergoing a pressure volume change, we have the equation delta S equals NR ln P2 over P1, that's P1 divided by P2, is equal to minus NR ln. Notice how when we flip P1 and P2, we get P2 over P1. Since we've applied the rule in mathematics of minus 1 times the ln of x equals the ln of x to the power minus 1. Well, this is the minus 1 of that. So when we substitute equation 3 into equation 2, you can see that delta S in this case is red. So I'm going to take this part of equation 3, substitute it in equation 2, and we now have a minus T multiplied by a minus. That gives you a plus. So we now have NR ln T, and the ln is P2 divided by P1. So we have a new equation here, or delta G. So in an isothermal process for chemical reactions involving ideal solutions, we can look at an equation, an equilibrium of A and B reacting to form C and D. And when the system is at equilibrium, remember, both rates are equal. And we're going to look at the delta G equation we can derive, and I'll show you how we're going to derive this in a minute. But the delta G in non-standard conditions is going to equal delta G under standard conditions plus RT ln, and again, if you look, it's the concentration of C divided by the reference, which is 1 mole per liter, to the power of C times concentration of D divided by 1 molar raised to the power of D divided by the concentration of A divided by 1 molar, again, since it's referenced to the power of A times the concentration of B divided by 1 molar to the concentration of B. So that's an equation you should be well familiar with. And now, since we're really dealing with activities here, it's the concentration of C divided by 1 mole per liter is really the activity of C. So another way of stating it is to say it's RT ln activity of C to the power of C times the activity of D to the power of D divided by the activity of B to the power of B times the activity of A to the power of A. So for a chemical reaction involving gases, this was for solutions. For gases, again, the same equilibrium. Our reference point now will be partial pressures divided by a reference pressure of 1 atmosphere, and we apply the same mathematics to it. So these equations, again, can be used to determine delta G under non-standard conditions, where the reactants and products are not in their standard states. So where do these equations come from? Let's take a look. So let's do some mathematics here. So let's assume the pressure is not at 1 atmosphere, and we have a reactant, NO, at a pressure other than 1 atmosphere, and it is changing into two products here, that N2O and NO2. And those two products, now we can calculate delta G for that reaction. And now when we calculate delta G, we can use an ingenious process to do that. So since delta G is in fact a state function, it means it's independent of the path we can use. So we can ingeniously create a new path to figure out what delta G would be when the system is not under standard conditions. So we can calculate a delta G1 using an equation that's been introduced to you previously. It equals the number of moles times R, the gas law constant, times temperature, times the ln of P2 over P1, where P2 is the final pressure, P1 is the initial pressure. And now what we're going to do is take the molecules of NO, and now they're at a reference pressure of 1 atmosphere. Well, we know how to calculate delta G changes when we're at the reference point of 1 atmosphere. We can use delta G equals delta H minus T delta S, or Hess's law, as we usually refer to it as. And we can calculate now the delta G2 when we convert during this chemical process, we're going to convert the 3NO to N2O and NO2. And then the third thing we're going to do is take those two substances that are now at 1 atmosphere of pressure, and now we're going to calculate delta G when we change the pressure back to the pressure that we want to use to calculate the delta G for this equation or reaction at the top. So we can add those 3 delta G's up in this multi-step process to arrive at the delta G for this particular reaction. And now we can see that we can use for delta G1, we can use the equation nRT ln the pressure it's going to change to is 1 atmosphere. The pressure it started with is the original pressure. And notice N is the number of moles. There's 3 moles of NO, so that's why there's a 3 in the equation. And we're going to add that to For the ease of simplicity, I've reordered the G1, G2, and G3. I've reordered them into G2, G1, and G3. And now we're going to calculate in blue here the G3, which is the delta G that we're going to find when the N2O is converted back to N2O from 1 atmosphere to the pressure that was used in the original equation, in the original reaction. Again, we're using nRT. In this case, it's 1 mole of N2O. Similarly, it's 1 mole of NO2. We're going to do it for both of those particular substances, and that's why there's 2 more terms here. One for the N2O, one for the NO2. Same equation we're using. In each case, the final pressure is what the pressure was in this equation, but the original pressure was our reference point of at 1 atmosphere. So now we're going to use some simple math here. We remember that y times the ln of x equals the ln of x to the power y. So now what we can do is take this 3, which is the y, and we can now put it as an exponent and change this equation here for delta G1 to RT ln 1 over the pressure of NO2, and it's now cubed. So since the other equations only have exponent 1s in them, and there's only 1 mole, I should say, only 1 mole, we don't need to make changes there. So now we're also going to use a mathematical equation, the ln of x plus the ln of y equals the ln of x and y, because we've got 3 different terms here that we want to reconcile. So now we're going to take out the common factor, RT, and now we're going to apply this rule, and we now end up with RT ln 1 cubed over the pressure of NO cubed times the pressure of N2O divided by 1 times the pressure of NO2 divided by 1. And now, hopefully, if you can see, we can take the 1s out. 1 cubed is 1, divided by 1, divided by 1. We're going to remove all those 1s. And now we know it's delta G plus RT ln P, the pressure of N2O, times the pressure of NO2 divided by the pressure of NO. Well, hopefully you can see from past lessons that there is a term we use to describe this relationship. The pressure of NO2 times the pressure of NO2 divided by the pressure of NO cubed. Well, isn't that equal to Q? So we end up with delta G plus RT times the ln of Q. And that is how we derive it from this multi-step process. We derive a formula to calculate delta G for pressures that are not at standard. So recall, what is a standard state? It's when a gas pressure is exactly 1 bar, which is an old pressure unit. A bar is defined as 100 kilopascals. If it's a solution we're using, then the solution will be at a pressure of 1 bar and its concentration will be 1 mole per liter. If it's an element in its standard state, it's what the element usually is at. It's what form the element takes at a pressure of 100 kilopascals or 1 bar and a temperature usually of 25 degrees Celsius. So for instance, if it was oxygen, it would be a gas. If it was sulfur, it would be a solid. When all components are in their standard states, delta G really equals delta G 0. Why is that? Well, let's take a look at this equation here. Okay, so this equation, delta G equals delta G naught plus RT ln Q. We've derived that equation just now, but standard conditions mean that RT ln Q really equals 0. Why? Because under standard conditions, if everything was 1 mole per liter, we're dividing by 1 mole per liter by 1 mole per liter, then you're going to end up with a value of Q of 1. So 1 mole per liter times 1 mole per liter divided by 1 mole per liter is 1. And then the ln of 1 is 0. Now, when the ln of 1 is 0, that means RT ln Q is 0, so delta G must equal delta G 0. Delta G at standard conditions, again, is what I call delta G 0. Delta G is delta G at non-standard conditions. Okay? So we can find delta G under standard conditions from tables in textbooks. Typically on evaluations, you are given those values. And at equilibrium, we're going to look at this system here. A and B, again, is in equilibrium with C and D. They're all aqueous substances, so dissolved in water. And again, we've derived this equation, delta G under non-standard conditions equals delta G under standard conditions, plus RT ln, and again, we're going to use the concentration of C divided by reference, concentration of D divided by the reference, and again, this will give us the value here, and we have the fact that at delta G, when it's equal to 0, the system is at equilibrium, and it means there's no energy available. So delta G is actually 0 in this case. Well, if delta G is 0 in this case, then we can now rearrange this equation. And if delta G is 0, we can simply take this term and move it to the left, and that makes it negative. So delta G under standard conditions equals minus RT ln C. This equation here, I don't need to repeat it again. And recall that really the concentration of C divided by reference and D divided by reference is all going to be activities. The activity of A, the activity of C to the power C times the activity of D to the power of D divided by the activity of A to the power of A and the activity of B to the power of B. So what we have is a very useful equation where delta G under standard conditions equals minus RT ln K at equilibrium. And in this case, K is equal to the equilibrium constant or concentrations, Kc, because this is the example we've just used. Now, for another example where we're using gases, we are going to use as our reference 1 atmosphere pressure. So again, we can derive this equation, and if delta G is 0 again, we can get a delta G 0 equals minus RT, because we're going to move that to the other side. This becomes 0. And again, these reference points really refer to activities. So it's minus RT ln activity of C to the power C, activity of D to the power of D divided by activity of A to the power of A times the activity of B to the power of B. So we end up again with another useful equation for gases. And in this case, ln K is going to equal the same as the K value, the equilibrium constant, which is unitless, is going to equal the Kp value at equilibrium. Kp is the equilibrium constant for gases. Okay, so now it's possible to calculate equilibrium constants from these two useful equations from calorimetric data. You don't need concentrations of solutions or partial pressures. So we're going to look at some examples where this becomes very useful. So we can simply say that delta G under standard conditions equals minus RT ln of Q. Now remember, Q can be calculated when the system is not at equilibrium, but when it is at equilibrium, Q is the same as K. Okay, so we're going to rearrange this equation now. And in terms of ln K, we're going to divide both sides by minus RT. So delta G divided by RT. And now we know the rules for natural logarithms. We're going to use the base E. So K, in fact, is going to be E to the power of minus delta G over RT. So if a system contains both solutions and gases, the K will not be numerically equal to either Kc or Kp. So if we take an example of an equilibrium involving both solutions and solids and gases, we can derive a K value by K is equal to concentration of hydroxide to the power 16. Notice we don't use sulfur, it's a solid, its concentration doesn't change. Similarly, the concentration of water doesn't change, so it's not involved in the equilibrium expression. And we're going to divide by, in this case, by the partial pressure of oxygen, raised to the power 4 times the pressure of, the concentration of sulfur to the power of 8. Now, we're going to talk about the activities here. So the activities, concentration of hydroxide has to be divided by 1 mole per liter since it's an activity to the power of 16, divided by the activity of oxygen. The partial pressure of oxygen divided by 1 atmosphere is the activity of the oxygen. And the sulfur ion here, we're going to divide its concentration by 1 molar since it's a solution. And again, note that this equilibrium constant is neither Kc nor Kp. It is, however, unitless. And I've mentioned that already, that those concentrations, since it's a solid and water liquid here in this expression, they don't change, so they're not included in the equilibrium expression. So now we're going to consider another chemical reaction. We're going to take NO and put it in equilibrium with N2O and NO2. And we're going to calculate the equilibrium constant for this reaction at 25 degrees Celsius. So note that if we use the equation we've derived, delta G equals delta G under standard conditions plus RT ln K. This delta G is at 298 K, which is 25 degrees Celsius. So at equilibrium, remember, delta G is equal to 0. So when delta G is equal to 0, we can rearrange this equation, take the RT ln K, move it to the other side, again, change its sign to negative. And now we can solve for ln K. So ln K is delta G divided by minus RT, which is minus delta G 0 over RT. And of course, now we're going to use our solution mathematically for lns. We know that the K is equal to E raised to the power of minus delta G over RT. So we are now ready to start solving this problem. We are going to take thermodynamic data from a textbook. When you're given questions like this, you'd be given the thermodynamic data. And we know from the balanced chemical equation, delta G under standard conditions is 1 mole of NO2 times 104.18 kilojoules per mole plus 1 mole of NO2 times 51.29 kilojoules per mole. That's the sum of the delta G's of the products. Now we're going to subtract the sum of the delta G's of the reactants, which in this case is going to be 3 moles of NO times 86.55 kilojoules per mole of NO. Well, when we solve this, we end up with a value of 104.18 kilojoules per mole. I'm going to caution you, because we're using this equation to calculate K, the R value will be given in joules. So we're going to change our 104.18 kilojoules, our minus 104.18 kilojoules, into joules by multiplying this by 1,000 joules per kilojoule. Okay? So we have to, now in this equation, we know delta G, and we're going to divide that by R times our temperature, which was 298 K, and our value is e to the power of 42.07, which equals 1.87 times 10 to the 18. Very, very large number, suggesting that this equilibrium produces a lot of product, very little reactant at equilibrium. So the reaction almost goes to completion here. Now let's talk about delta G and the extent of a reaction. So because delta G is equal to minus RT ln K, and K equals e to the power of minus delta G0 divided by RT. We know if the delta G0 reaction, if that value is large, and if it's negative, it means K will also be a very large number, the equilibrium constant. This means there's way more product than reactants. So if we start with reactants and go to products, this will be an equilibrium that favors the product. It will be significantly shifted to the right if, again, delta G is large and negative. Now, the reverse is true if delta G is positive. K will be very, very small. Now, if it's a large number that's positive, K will be very small, which means this equilibrium favors the reactant rather than the product. It means most of the equilibrium will remain in the state of the reactants. There will be very little product produced. And the third example we'll talk about is if delta G is close to 0, then K is close to 1. This means you have similar amounts of reactants and products at equilibrium. So recall the graph of how temperature influences delta S, delta H, and delta G. We are now going to look at the temperature dependence of these equilibrium constants. So how does temperature affect the value of K? Well, we know in this equation, temperature is in this equation. It looks like it influences delta G, and surely you can see that from this graph. As temperature changes, delta G changes significantly. Okay? Whereas delta H and delta S hardly changes at all. So we, again, can use our knowledge of equations and go delta G, in addition to being equal to minus RT ln K, is also equal to, when delta G0 is delta G under standard conditions, it's going to equal delta H under standard conditions minus T times delta S under standard conditions. That's an equation we've looked at before. We're going to call that equation 1. And both delta H and delta S, like I've said, are pretty well temperature independent over that temperature range. They don't change hardly at all. Okay? And K is affected by temperature in this equation. So if we now take this equation, equation 1, and divide both sides by minus RT and do some canceling, minus RT cancels here, temperatures cancel here, we end up with a pretty useful equation that says the natural logarithm of the equilibrium constant K equals delta H0 divided by R times 1 over T plus delta S over R. And that second equation can be used. Okay, now if I take that second equation and I graph the relationship between the ln of K versus 1 over the temperature, what we can get is a linear relationship. And this linear relationship, remember, is very useful because it's just like the equation y equals mx plus b. We can use this equation. The slope of this line, m, and x in this case is temperature, or 1 over temperature. So the slope of this line is delta H0 over R. The y-intercept is delta S0 over R. Just like, again, y equals mx plus b. B is the y-intercept. M is the slope of the linear relationship. So once the temperature dependence of K is graphed, we can use it to predict of any value of K at a different temperature. Assuming that delta H0 and delta S0 are constant over the temperature range being investigated, because we looked at that graph on the previous page, and you saw these were constant, delta G is changing. So now we can have another path to finding K. So we can find K algebraically at different temperatures doing the following. We can now know that at one particular temperature, we know the ln of K1 equals this mathematical relationship, and the ln of K2 at a different temperature, T2, is this equation. Now, if you subtract equation 1 from equation 2, and remember, the ln of x minus the ln of y equals the ln of x divided by y, you end up with this very useful equation here. The ln of K2 divided by K1 equals minus delta H 0 over R times 1 over T2 minus 1 over T1 for our two different temperatures. Now, this equation is named for a man called Van 't Hoff, or a woman, not sure which, and you can use it to calculate K at any temperature. Once you calculate delta H naught from thermodynamic data, and you have a K value already calculated at a different temperature. So now let's look and see how we can do this, okay? We're gonna look at a second way of calculating K. If you have data from thermodynamic tables, you can calculate delta H and delta S under standard conditions. Remember, delta G is delta H minus T delta S. And if you put delta G naught into this equation, you get K is equal to E to the power of delta G naught, or delta G 0, I say naught sometimes, divided by RT. We can find K. So let's look at how to do that in this particular chemical reaction. So we've got an equilibrium here of carbon and water, an equilibrium with hydrogen and carbon monoxide, and we'd like to calculate delta H naught, delta G naught, K at 298, K at 1298, so at two different temperatures. So we can use Hess's law to calculate delta H at 298. We have tables that give us that data. So in this case, you're going to look at the delta H for hydrogen and multiply by 1, add it to the delta H of CO multiplied by 1. That's the sum of the heats of formation of the products. And then you're going to subtract the sum of the heats of formation of the reactants. And you end up with a value of 131.3 kilojoules per mole. I'm going to change that into joules because, again, we want to have units that are compatible with each other. Now we can calculate delta G the same way from thermodynamic data from tables. It's the sum of the delta G naughts of the products minus the sum of the delta G naughts of reactants. And we can calculate that easily. And now we know we can calculate the K at 298, the temperature at which all this data was gathered for. So we know that it's equal to E to the power of delta G naught over RT. So we can substitute our values in. That one's for delta G, 91,440 joules. And RT are those values. We end up with E to that power. And that number tells us that this reaction is not product favored. It's reactant favored because it's such a small number. So now let's see. So the reaction barely goes. So let's see what happens at another temperature at 1298. We can use, again, the Van 't Hoff equation, and we can say the ln of K2 over K1, and we're trying to now to find K2. We know what K1 is. This is K1. Is going to be equal to the delta H value divided by R, and we're going to now multiply it by the difference in those inverse temperatures. So again, T2 is 1298 K, T1 is 298 K. When we solve that equation, we end up with 40.85, equal to the ln of K2 divided by K1. Now, when we apply the rule here in mathematics, the ln of K2 over K1 is equal to K2 over K1 equal to the E value raised to the power of 4085. Well, now we know what K1 is. Here's what K1 is. We can substitute K1 in this equation, and now we can cross multiply, and we end up with K2 equals K1 times E to the power of 40.85. And that number, again, there's K1, there's E to the power of 40.85. We end up with a value of 51.4. So at a higher temperature, at 1298, we see this reaction will go. Now, the suggested homework, here it is. And I thank you for staying tuned. Signing out.